Hey everyone, welcome to Newton's Method. This is Nicholas JMV. So Newton's Method is pretty easy to understand. It can be a little tricky to use, especially when we get into some of these decimal problems. So what Newton's Method does, it uses tangent line approximations to estimate a zero of a differentiable function. This method may not always work, especially if you think about using a horizontal tangent. So what this means is that we're going to try to estimate a zero from a differentiable function. Say it's right here. And so what we get to do is we kind of get to pick our first estimate and kind of say maybe we want it to be, right here. And this is our x sub 1. Okay, so what happens is we go up here and it hits our graph and it's not a zero, but we get this nice tangent line approximation. So we draw a tangent line here. Okay, and it goes down and we get this other zero. Now it's getting pretty close. And then we see what value that actually is on the graph. And then we have another approximation going back the other way. And so the more approximations we use, you can see the closer we're getting to our zero. So that's what Newton's method does. It uses linear approximations, tangent lines, to approximate the zero of a differentiable function. So how you do this mathematically is you have your estimate, okay? You want to pick one that's pretty close to what you think the critical value is, okay? And so to find x sub 2, you just take your x sub 1 value and you subtract from that f of x sub 1 divided by f prime of x sub 1. So once you get that answer, if you want the third iteration, they're called, the third iteration is taking your answer from the step above and subtracting off f of x sub 2 divided by f prime of x sub 2, and so on and so forth. So what you need is, you need the function, you need the derivative. So let's go ahead and look at examples, see if we can figure this out. Okay, so now I'm going ahead and graph this function for us because it just makes it a little bit easier. So find where f of x equals x cubed minus 5 intersects the x-axis. Find the solutions to at least 6 decimal places. Okay, so I've gone ahead and graphed this function, and you notice that at 1, okay, we have a negative number. At 2, we have a positive number. So between 1 and 2, we know that the graph crosses the x-axis. Okay, so I can either pick 1 or 2 to estimate. So what I'm going to go ahead and do is I'm going to pick the value of 2. Okay, so 2 is going to be my estimation. So let's look at how we do this problem now. So you really don't need the graph from here. We know that f of x is x cubed minus 5. So we're going to go ahead and let's go ahead and write that. So we have f of x equals x cubed over 5, or minus 5, excuse me. And we know that f prime, using the power rule, is just 3x squared. We're going to choose x1 to be 2. Okay, we're estimating. So let's go ahead and start this iteration. So we know that x1 is 2. That means x sub 2 is equal to x sub 1, which was 2, minus f of 2 over f prime of 2. Okay, so that's going to equal 2 minus f of 2. 2 cubed is 8, minus 5 is 3, over f prime of 2. So f prime of 2, so 2 squared is 4, that's 12. Okay, so we get 2 minus a quarter, which is 1.75. Okay, not too bad there. So let's go to the next iteration. So what this is guessing now is our 0 is 1.75. That's what this number would represent. So let's see if we can get it closer. So let's go x3, the third iteration, right? The next iteration down. Iteration, excuse me. So I take 1.75 minus f of 1.75 divided by f prime of 1.75. Okay, so that's going to equal 1.75 minus, and when I get this, I get 0.359375, okay, divided by 9.1875, and when I get that approximation, I'm at 1.71088 0.435. So notice how that drops off, okay? So this drops off, and now I go from 1.75 to 1.71000 or 0.88435. So I'm getting even closer to that value. So now if I wanted the next one, the fourth iteration, now I keep going. How long do I keep going? Well, until this number starts to become really consistent. So we're going to take that number, I'm going to round it a little bit here, 1710884. Okay, and I'm going to subtract off f of that number, 1.71084 over f prime of 1.710884. Now I'm plugging this number into way up here into the f of x, and this number, same number, into here. And so when I simplify that and I use my calculator here, I get approximately 1.709974. Okay, so you can see pretty consistently, and if I went one more iteration after this. I'm not going to go ahead and do that, but when I got to the fifth one, I was approximately 1.709060824. So you can see that zero from my graph, this zero right here, is approximately 1.70. Okay, so that is using Newton's method, okay, in order to find the zero of a differentiable function. So if you have any questions or comments, go ahead and type them below, and we'll see you next time.